Good morning, and what a fantastic start to reInvent 2024. Welcome to this session on reducing foundational model deployment costs and latencies with Amazon SageMaker. My name is Venkatesh Krishnan, and I lead product management for SageMaker. Joining me in this talk today is Amit Arora, who's a principal AI and ML solutions architect at AWS. And it's our immense pleasure to have Grant Guillory, VP and distinguished engineer from Capital One, who will be talking to us today about how Capital One have successfully leveraged SageMaker for their model hosting needs. So let's get started. Artificial intelligence and machine learning, especially generative AI, is revolutionizing business strategies. And our customers are increasingly harnessing this technology to deliver personalized, immersive, and unique customer experiences. Let's dive right into the heart of AI and ML, which is machine learning inference. In this session, we will explore how you can maximize your return on investment by achieving optimal performance at the lowest possible cost for hosting machine learning models. We will begin this session by examining two of our fully managed inference capabilities in AWS, which is Amazon Bedrock and Amazon SageMaker. In this presentation today, we will dive deeper into SageMaker inference. We will showcase several SageMaker inference capabilities that will help you achieve the lowest inference latencies, highest throughput, and optimal cost alignment with your business objectives. We will discuss the inevitable trade-offs, and we will show how you can optimize your SageMaker endpoint deployments very efficiently. To bring these features to life, we will show you a demo where you will learn how to use these features and you will see them in action. And finally, we will hand it over to Grant from Capital One, who will share their success story of deploying models on SageMaker for inference. And we will conclude this with a Q&A session. So when it comes to deploying AI models on AWS, customers often find themselves leveraging both Amazon Bedrock and Amazon SageMaker to address a diverse array of use cases. So these two services offer distinct approaches to model access and model deployment, each with its own strengths and ideal scenarios. So Amazon Bedrock is best suited for situations where serverless deployment is preferred. With Bedrock, there is no need to worry about provisioning instances or configuring your infrastructure or setting up auto-scaling. It's all handled for you by the service.
Take a picture when I'm speaking.
It offers pre-trained models which can be fine-tuned. So Bedrock provides a good balance of customization and ease of use. Pricing on Bedrock is token-based with options for on-demand and provision throughput. On the other hand, SageMaker is the go-to choice for those who need more control over their deployment infrastructure. It is server-based, allowing users to fully configure the managed infrastructure for their models. SageMaker also allows you to bring your own model, and the pricing is instance-based, so you pay for the compute. Oh, the audio is lost. Is it back? OK, sounds good. Thank you. So let's double-click on SageMaker Inference. SageMaker Inference offers a configurable software and hardware stack, giving customers high visibility and granular control over your machine learning infrastructure. Deploying models on SageMaker for inference involves three key steps. The first step is for you to create a SageMaker model object by specifying the model artifact and the inference code. Then the next step is for you to configure an endpoint. And this is where you will specify the compute resources and the scaling options. And finally, you will deploy the model to an endpoint and make it available for real-time inference. With access to over 100 instance types, including CPUs, GPUs, and specialized AI accelerators, you can precisely match your compute resources to your model's needs. You can also enhance your inference by adding custom pre- and post-processing steps, which allows for, say, for example, data transformations or result formatting, or maybe you want to implement some custom business logic. To make your deployments easy, we offer you several ready-to-use containers that come pre-packaged with the latest libraries and runtimes for inference. Also, you can start with these 1P images, the images that we provide, and you can customize them by adding your own libraries or proprietary software. For complex use cases, SageMaker allows you to deploy multiple models onto a single endpoint, and this facilitates more efficient resource utilization and simplified management. As you consider deploying models at scale, you will have to strike a balance between three factors so that you can achieve the best performance at the lowest possible cost for building your Gen AI applications. These three factors are complexity, performance, and cost. Complexity manifests itself in terms of the size of the model, or perhaps you have an ensemble or a system of models or chain of models that you want to deploy together. Cost is an important consideration, and you want to minimize not only the cost of hosting the model, the infrastructure cost, but also the cost of operational overhead. And then there is performance, right? So if you're building an application which is highly interactive, then you want to minimize the latencies, the inference latencies, to just a few milliseconds. If your application is serving millions of end users, then you want to achieve high throughput for your inference. Now, these three factors, performance, complexity, and cost, often pose a trilemma, which means that you can choose two of these factors to meet your business requirements, and then the third one becomes quite difficult to optimize. So for example, let's say that you want to deploy a very large model, and you have very stringent latency or throughput requirements, then you will have to deploy the model on expensive GPU-based instances, so your costs shoot up. Or let's say that you have a very tight budget, yet you want to build an application that demands low latency, then you want to consider hosting a smaller model that is fine-tuned for a specific task, or use model distillation techniques. With all the flexibility that you get on SageMaker, you get a lot of levers to achieve the right trade-offs that you need in order to meet the business objectives. So today, we will dig a little bit deeper into all the features that are available on SageMaker that can help you achieve these trade-offs more efficiently. Let's start with features that help you save deployment costs. SageMaker offers a powerful solution for cost-effective model deployment. So this feature allows you to host multiple models, multiple foundational models on a single endpoint so that you can use the accelerators that are available on the instance more effectively. For each model that you deploy, you can allocate a customized number of machine learning accelerators, and SageMaker will handle the placement of the model containers onto the accelerators to maximize the hardware utilization at all times. So what this means is that when the number of copies of the model scales up in response to growing traffic, SageMaker will automatically place the model on accelerators that are available on existing instances before it goes ahead and adds a new instance. Likewise, during scale down, SageMaker efficiently bin packs the models, relocating the models seamlessly if needed in order to save costs. Recently, we launched 3 new features that will help you save even more costs, and let me introduce them to you. First, we made auto-scaling much, much faster. So with the new infrastructure innovations that you get out of the box on SageMaker, and you get this without having to do anything, you will notice that auto-scaling latencies for popular foundational models is over 58% lower than before. So by scaling faster, SageMaker allows you to minimize how much you need to over-provision to account for slow scaling. Second, and this one is a big cost saver, you can now set auto-scaling policies so that your endpoints can scale down to 0 instances when there is no traffic. This means that you can configure your SageMaker endpoint so that you don't have to pay for instances when there is no traffic. And when the traffic resumes, after a pause, the endpoint will automatically scale up to serve new traffic without any intervention. A third feature that we launched recently allows you to host thousands of fine-tuned flavors of a model on the same endpoint, saving thousands of dollars in cost. Let me explain how. Fine-tuning techniques such as PEFT and LoRa have gained popularity for their efficiency in adapting a large language model by training only a small subset of parameters, right? These parameters are called adapters. This approach allows you to create thousands of fine-tuned flavors of a base model. SageMaker now offers you a cost-saving feature that allows you to host the base model and all the fine-tuned flavors onto the same endpoint and on the same instance. So this easy-to-use feature includes lifecycle management APIs for the adapters, usage monitoring for each adapter, and auto-scaling of the base model in response to traffic. This innovation significantly enhances the flexibility and cost effectiveness of deploying customized AI models at scale. Next, let's switch gears and talk about how we can optimize performance of your model on SageMaker. So we'll walk you through some of the features of SageMaker that will help you reduce inference latencies and improve throughput. There are two ways you can reduce end-to-end latency. First, by routing the requests more efficiently to the copies of the models behind the endpoint, and second, by running inference faster. Now let me highlight the features in SageMaker that can help you route your requests more efficiently to your models. First, there's a feature called load-aware routing. Let me take a step back. By default, SageMaker endpoints use random routing strategy, which means as the traffic comes to your endpoint, SageMaker will randomly route it to the copies of the model that are behind the endpoint. But with the new load-aware routing strategy, you can set this using a flag when you configure your endpoint. SageMaker now can keep track of which copies of your model are currently serving traffic and route requests to copies that are available to serve new requests. And this can reduce your inference latencies by over 20%. A second feature is what we call as session-aware routing. Some of us also call it sticky routing. So if you enable session-aware routing, all requests for the same session will be routed to the same copies of the model, and this will allow your ML application to reuse previously processed information. So this can reduce the latency and improve user experience. And you will see a demo of this a little later. Now let's explore how you can optimize your machine learning models to run faster. SageMaker offers you an inference optimization toolkit that provides a menu of cutting-edge technologies, such as speculative decoding, quantization, and compilation that speed up inference. So you will benefit from out-of-the-box support for scalable, performance-tested speculative decoding, quantization for various model architectures, and efficient compilation with optimized model loading and caching. Here are some of the performance and cost numbers based on our benchmarks using the OpenOrca dataset. So on an average, you will see that you can achieve 2x improvement in throughput and 50% lower cost for Llama 3 models when you use the out-of-the-box optimizations that we offer you on SageMaker. Now it's time for us to see some of these features in action. So let me welcome my colleague Amit to demonstrate these features.
Thank you, Venki. Good morning, everyone. Welcome to our session on reducing FM deployment cost and inference latency through Amazon SageMaker. My name is Amit Arora. I'm a principal solutions architect for AI/ML and generative AI at AWS. Now, in the course of next 20 minutes or so, I would be presenting to you demos for some of the inference optimization capabilities that Venki just talked about. The code for all three demos that I would be presenting is available in an open source GitHub repository. So the QR code that you see on your screen refers to that repository. I would highly encourage you to scan that. It has some very useful code samples that you can use at a later date. With that, I see some people still scanning it. With that, let's get started with the first demo that we have for you today. And that is, the first demo that we have for you today is for SageMaker sticky session routing. Now, oftentimes we want to build state-aware AI/ML applications. So let's say if we have a large multimedia asset such as a picture or a long multi-turn conversation. Now we want to run repeated inferences on this data asset, but that takes time because this large data asset needs to be loaded again and again into the GPU memory. And we want to reduce this time so that we can get a better inference latency for a real-time workload. That is the problem that the sticky session routing solves. There are two aspects to this problem. The first part is making the model server aware that this data asset is linked to a particular session ID. So we do that using the PyTorch torch-serve model serving container. We'll see that in action. And then a SageMaker endpoint can be backed by multiple instances behind that for, let's say, scale or availability reasons. So SageMaker would then be able to route your subsequent request to the exact same instance to which the session was first initiated with. The combination of these two is able to give you much optimized inference latency when you are referring repeated inferences to the same data asset. Let's run some code now. Okay, so what we have for you is a recorded demo. Now, I like live demos just like every other person sitting here, but we thought that we're not going to risk unknowns on the first day of reInvent at Monday morning at 10 a.m. So I'll be providing a voiceover to this demo. You see my picture on the screen, so I actually did run this code, so it all works. You have the code in GitHub. So let's get started. What you have here is a Jupyter notebook. We will be using sticky session routing with the Lava model, the large language and visual assistant model. We start with building a custom Docker container. We start with the PyTorch torch-serve model server, and we are now going to add some custom code to that and build a custom container so that it is able to download the model weights from Hugging Face. So now I have already done that. This process takes about 5 to 7 minutes to do that. The highlighted base image that you see on your screen is a publicly available image on Amazon ECR. The custom code that I was referring to you, which refers to the sticky session routing, is available as part of this code repository. Now, this code that you see here is generic enough. So if you want to use this code with some model other than Lava, you would be able to use it as it is with no changes in the code. So we are going to build the custom container. Like I said, the commands are also provided here. It takes about 5 to 7 minutes to build that container. So now we've already built that container in the instance of time, and this once again is the base image that we use for building the container. Now, once the container is built, the next step is to use the Torch model archiver to use this code that is provided here so that this code is now uploaded in an S3 bucket. This could be an S3 bucket in your account. Now, we are going to use the custom container and these files included in this repository, which provide the sticky session routing implementation into an S3 bucket. So this is the S3 bucket on which the custom code is now available. The custom model we have built contains the model binaries. We are now at this point ready to deploy this model on a SageMaker endpoint. So we'll do that using the SageMaker SDK model class. We are going to deploy the Lava model on the MLP4D 24x large instance. What I would highlight over here specifically is the environment variable section of this model serving call. Now you see here, there are a few new headers, the X Amazon SageMaker session ID and start session indications. This is how SageMaker is able to convey to the torch-serve model server that I want to link this particular inference request with a particular session that torch-serve has created. It is through these custom headers, and SageMaker is now going to pass these custom headers in all subsequent calls so that the torch-serve model container can link these subsequent calls to the data asset already loaded in memory. So again, these are the highlighted new headers. Other than that, there is absolutely no change in that model object that you saw on your screen. So once the model object has been created, we call the model.deploy function. There is absolutely no code change in the model.deploy. This is how we regularly deploy models on SageMaker. Once the model object has been created, we are now able to create a SageMaker predictor object. This predictor object is going to be used to run repeated inference on the model endpoint that we have just created. So now we are ready to run the inference on that. There is some code that is available in this repository, which translates the API request into an SDK format that SageMaker understands. And again, all of that code is available here. The interesting part, which we now jump into, is this image that you see on your screen. We are going to run repeated inferences on this image. Now, this is a publicly available image. The image URL refers to an HTTP URL. You could change that to refer to any image on which you want to run an inference on. Now, this is a publicly available image. Now, we are going to run repeated inferences on this image, and the expectation is that while the first inference takes some time, the subsequent request should be much faster because now this data asset has been loaded into the memory. We are going to use the SageMaker invoke endpoint function to run inference on that. The new parameter that refers to sticky session is this session ID variable that you are seeing here. This session ID would be provided to us by the torch-serve container once we create a new session. So if you see this highlighted code, we call the send and check response and pass it a special string called new session. This tells the torch-serve container that I want to create a new session and I want to link this session with the image URL that I'm providing over here. So every subsequent inference request that I send to torch-serve, which refers to this session ID, can now take advantage of the data asset that is now already loaded into the memory and work much faster. So we are now ready to run our first request. So we've created the session, and the highlighted session ID shows you the session ID or the sequence ID that torch-serve has provided to us. So we send our first prompt, and in this prompt, we say, describe this picture, and we are asking it to generate a bunch of tokens. And notice that we pass the session ID to this inference request. So when we run this request, we will see that it takes about 5.5 seconds or 5.39 seconds to describe this picture. This is, again, the Lava model running inference on that image that we have uploaded. So it takes 5.39 seconds to do that. The next request that we are going to run, which we ask a different question, is there grass in this picture? And if so, describe it. The expectation is that this request would run much faster because the data asset is now already loaded into the GPU memory, and we are simply referring to it as part of this request. We don't have to upload this image again. So when we do that, we find out that it takes just 1 second to generate the same amount of tokens. This is our second inference request. So 5.39 for the first one, 1 second for the second one, and then we can continue this procedure. We ask it another question through another prompt, and this time, again, it takes 1 second to do so. So this is sticky session routing for you, where SageMaker, in conjunction with the model server, is able to refer subsequent inference requests to an already established session ID. So once that is done, once our inferences are done, we are now ready to close the session, and we do that by passing it a special close session header. Once we do that, this data asset is now ready to be removed from the GPU memory, and then we can go ahead and delete the endpoint if we want to. So again, to summarize, sticky session routing, we went down from 5.39 seconds to just over 1 second for subsequent inference. That was our first demo for today. So the next two demos that we have for you belong to a category of optimization called ahead of time optimizations, or AOT. Now, the demo that we saw previously was happening at inference time. The optimization was happening at inference time. But with these two techniques here, and Venki also referred to them in his presentation, speculative decoding and quantization, the optimization happens ahead of time, at the model deployment time. So there are two techniques we are exploring. One is called speculative decoding, where we take a much smaller model. So let's say we want to run inference against a Llama 370B model, but we will take a much smaller, what we call a draft model, such as a Llama 3.8B, and ask it to generate the tokens. And we are saying that we expect that these tokens to match what the larger model would have generated. So we'll see that in action. And the second technique that we will be looking at is quantization, where we store some of the model weights in lower precision format. So let's say instead of floating point 16, we would be storing those model weights in int 8 or integer 4 format, and thus saving hardware costs because we can now load the model on a much smaller instance. So we'll be seeing these two demos in action now. Okay. If it moves to the next one. Okay, there you go. So the first demo, or rather the second demo that we have is for speculative decoding. Now, speculative decoding is a technique that has been described in multiple papers, such as this one. The idea behind this being that large autoregressive transformer models are slow because if we ask them to generate K tokens, they run K passes on the model in a serial fashion. So if it's a very large model, this is going to take some time. So what we do in this technique is that we use a much smaller draft model, and SageMaker provides an optimized draft model for several models. We'll be doing this example with Llama 370B. So we'll take a much smaller draft model and ask this model to generate multiple tokens in parallel. And then rather than having the larger model generate all the tokens, we simply ask the larger model that are these tokens acceptable? Now, the larger model may accept all of these tokens in which case we would get extreme optimization, 50 to 60%. Or the larger model may accept only some of the tokens, and it may reject the rest of the tokens, in which case the larger model then generates the remaining tokens. Or in the worst case, the larger model will say, I will not accept any of these tokens, and I'll have to generate all these tokens myself, in which case you get no optimization. So in that sense, no harm, no foul. So we'll be doing this demo in 3 parts. We will first run the Llama 370B model in an unoptimized fashion and see what is the inference latency we get, what is the output it generates. So we'll note that. In the second part, we will say we are now going to run a optimized version of Llama 370B, which uses the SageMaker provided draft model. And expectedly, we will see that it provides a much better inference latency. And in the third part of this demo, we can see that this draft model that I'm referring to can also be a custom draft model, which means you could download another different model from Hugging Face or even fine-tune your own model on SageMaker and use that as a draft model and see if you are still able to get a reduced inference latency. So it's a 3-part demo. So this is a feature that we call speculative decoding. So let's get started with that. As soon as we are able to set up some of the libraries and import those SageMaker packages, we will be able to deploy this baseline model. Almost there. So we are setting up the SageMaker, updating the SageMaker SDK, importing some packages, and we are again going to deploy the Llama 370B on the P4D 24x large instance. So you see this model ID highlighted here. This model ID is being provided by SageMaker Jumpstart. Now, for SageMaker Jumpstart, we have put the model binaries in a world-readable S3 bucket so that we can load them faster rather than having to download them from Hugging Face. And this is the sample input on which we would be running inference. So we are going to ask this model to generate 128 tokens. Note the time it takes to generate that. Note the tokens that are generated. So that would be our baseline. So this first step we do by creating a model builder object. So we create a model builder object which is provided by SageMaker. We pass it simply the Jumpstart model ID. And now we are also able to display some benchmarking metrics. So just as an aside, when you want to run large language models on SageMaker, you are obviously interested in finding out what is the performance of these models on different instance types. So we've provided some benchmarks as part of the model builder itself so that you can see that what response times would I get, what throughput would I get if I host it on a G5 48x large instance, and what response time and throughput I would get if I host it on a P4D or a P5 48x large instance. So just some guidance for your workloads. Now, if you have a large number of concurrent users, you might want to deploy it on a P5 versus if you have a small scale workload, you can save some cost by deploying it on a G5 48x large. That being said, we are now at the interesting part of the demo. So we deploy this model by using the set deployment config, and we say config name is LMI. LMI stands for large model inference. This is the unoptimized version of the model that we are deploying. So we'll deploy this model, and SageMaker now knows that, oh, I have to deploy this model. Here are the model binaries in S3. This is the inference server I have to use. We'll create the model builder object using model builder.build. And then deploy this model as usual on a SageMaker endpoint. Once we do that, we will be ready to run inference. The model binaries, again, are available in S3. So we call the model builder.build, and then we are going to call model builder.deploy. This process takes about 7 to 8 minutes to deploy a Llama 370B model. And once the model is deployed, we are ready to run predictions on the sample input. In our sample input, we were generating 128 tokens and noting the time to do that. So it took about 6 minutes, 33 seconds to deploy this model. And now we are ready to run inference on this sample input. So once we run this cell, we will see that it takes about 4 to 5 seconds to generate these tokens. So it takes 4.5 seconds to generate 128 tokens. Now this is our baseline performance. This is Llama 370B with no optimizations deployed on SageMaker. Now in the next step, we will say, OK, we will delete this endpoint since we are done with this. And we are going to now deploy this same model, but this time optimized with speculative decoding, and hopefully get a much better inference latency. So we'll move on to the next step once we delete the endpoint. And we will create the model builder object as before, absolutely no change in code. tell the model builder, this is my model ID, this is my schema, display the benchmark metrics as usual if we need to. And once that is done, we will set the deployment config. Instead of saying LMI, we are this time going to say we set the deployment config to LMI-optimized. This is what is going to tell SageMaker that I want to deploy a optimized version of this model, i.e. with speculative decoding using a first-party draft model that SageMaker provides. So we'll deploy that model just one single parameter change. So that's what I wanted to illustrate how easy it is to deploy one with speculative decoding, just one word in the parameter change. We'll deploy this optimized model. Again, it will take 6 to 7 minutes to deploy. Once the deployment is complete, we are going to be able to run inference and then see that we are able to get inference in much less time. So we are going to run optimized model.deploy. It takes about 7 minutes to deploy that model. Once that is done, we are going to run inference on that and see that this time we are able to get inference in almost half the time. So we run the same predictor.predict on the exact same sample input. And this time, instead of 4.5 seconds, we got the output in 2.66 seconds. So almost a 40 to 50% improvement in inference latency. We are generating the exact same tokens, but we are able to do that in a much shorter amount of time. Now, in the interest of time, I'll skip to the next demo. Just mention here that we can use this exact same code to take a custom model, which we will download from Hugging Face, and use that as a draft model. So if you want to use a different open source model or fine-tune your own model and use that as a draft model, again, it's a single parameter change to the code that we saw, and you'd be able to use that. What we find out over there is that the open source Llama 3 8B actually provides inference latency of 3.6 seconds as compared to 4.5. So still improvements from what we initially got without speculative decoding, but it is not as good as the SageMaker provided draft model where we were able to get 2.66 seconds. So just to recap, 4.5 seconds was the unoptimized model. 2.66 seconds was the speculative decoding with the SageMaker provided draft model. And if you run the demo completely, you will find out that the open source Llama 3 8B provides 3.66 seconds. So some improvement still, but not as much as what you get with the SageMaker draft model. So with that, we'll quickly jump over to our third demo. The third demo refers to model quantization. Now, you may have heard about model quantization. There are several papers on it. We are going to use one form of quantization called AWQ, which has been implemented in SageMaker. AWQ stands for Activation Aware Weight Quantization, where we say that we are going to be saving the model weights not as floating point 16s, but we can change some of the model weights to be integer 8 or integer 4, and thus the model size becomes much smaller. What this then enables us to do is deploy the model on a reduced hardware. So in the previous two demos, we saw that we were using a P4D 24x large machine, but in this demo, with the quantized model, we will see that we are able to deploy that same Llama 370B on a G5 12x large machine. So a much smaller machine. This is the paper that I was referring to, Activation Aware Weight Quantization. So we get 4 advantages by using this technique. Reduced hardware, increased space for KV cache, and faster decoding latency. The process for deploying this model with quantization is exactly the same. We create the model builder object as before. Now we are going to run the model builder.optimized. And in that model builder.optimize, we are able to provide one single parameter which says optimize option quantizes AWQ, referring to activation aware weight quantization. So we save the new model weights in this S3 path that you are able to provide here. Now the quantization process, since it's going to change a lot of model weights, takes about 2 hours, or in this case, 1 hour and 54 minutes. And this new model, which is the quantized version of the original Llama 370B, is available in this S3 bucket. We are now able to deploy the model as before, just that we are now going to deploy the model on the G5 12x large. Now, just for contrast, the G5 12x large contains 4 NVIDIA A10 GPUs, whereas the previous instance that we were using was the P4D 24x large, which contains NVIDIA's A100 GPUs and 8 of those. So it's quite a big shift, just to illustrate that we are able to use a much reduced hardware requirement, much reduced hardware instance to deploy this model. So it's going to be much cheaper to host this model at scale if we are using the quantized version. Once the model is deployed, takes 6 minutes or so, we are going to run the same sample input as before, ask it to generate the same 128 tokens just for performance benchmarking reasons. And we are able to see that when we call the predictor.predict, it's able to generate these tokens in roughly the same amount of time. So imagine the amount of savings that you are able to get by shifting from a P4D 24x large to a G5 12x large instance. So that was the third demo that we had for you today. So just to recap, we went through 3 demos. The first one was sticky session routing. The second one was speculative decoding. And the third one was quantization. So in all 3 demos, we saw that there was a significant reduction in inference latency. So with that, it's our extreme pleasure to invite our esteemed guest from Capital One, Vice President and Distinguished Engineer, Grant Guillory.
Thank you, Amit. All right. Can everybody hear me? Awesome. My mic has been switched out a couple of times at this point. Hi, everybody. My name is Grant Guillory. I lead software architecture for Capital One's ML platforms. And let me get to the right spot there. So today we're going to talk a little bit about how we've integrated SageMaker inference into the back end of our platforms. And we're going to talk a little bit at a higher level than we've spoken about up until this point. But before we do that, I want to set the stage. Some of you may not know much about Capital One. And I'm going to tell you a little bit about the context of our AI and ML journey. So one thing, as you all probably know, we're both a credit card company and a bank. Banks are not always known for being at the forefront of technology, but Capital One is an exception. If you look at what we've been doing over the past couple of decades, Capital One has been on a significant transformation journey on both our technology infrastructure as well as our talent. At this point in time, we built an in-house organization of over 14,000 technologists with 4,000 granted patents. We've rebuilt our tech stack and infrastructure, going all in on the cloud, and it continued to stay at the frontier of cloud innovation, leveraging serverless technologies in over a third of our applications. We've also transformed how we build software and become an early adopter of APIs, microservices, DevOps, and automated testing and deployment. In addition to that, we've built a modern data ecosystem on top of AWS infrastructure focused on data products. Now we are starting to drive convergence across our organization to enterprise platforms to enable automation, standardization, and scale across many different use cases. All of this has set the foundation for our AI and ML journey. At this point in time, we have AI and ML use cases in production across nearly all of our lines of business, driving value for 100 million customers and 50,000 associates. Everything from fraud prevention to personalized customer experiences to developer assistance, and much more. A couple of examples of different Capital One products that you may or may not be aware of. If you think about fraud detection and you look at our credit card offerings from things like VentureX, this is sitting behind the scenes. If you think about all of the mobile applications that we have, those personalized experiences are making sure that they are right for you based on your particular context. But now we're going to talk a little bit about the next stage of our AI and ML journey. So everyone here is aware, and given both Venki and Amit's talks about foundation models, the emergence of FMs, specifically starting in 2017 with transformer-based models, and then in 2022 with multi-shot learning and ChatGPT, changed dramatically the scope of the space for model development. It enabled entirely new classes of both internally facing as well as externally facing applications. While we already had AI and ML at the core of many of our products, FMs expanded that scope even further. And it also requires us to build new infrastructure. So early last year, we embarked on a journey to enable this new technology. As the number of use cases expands, rather than training, inference in this context becomes one of the key differentiators in terms of delivering production applications and ensuring that all of our use cases are production ready. And as a platform-centric organization, this meant building a platform to enable this, ensuring that we both are well managed and can scale across the entire enterprise for a large number of use cases. So before I dive into the solution, I want to talk a little bit and ground us in some of the changes that have happened in the AI and ML stack. On the left-hand side, you see a relatively simplified version of an ML stack. This is at the low end of simplicity, but in many cases, if you're talking about like tree-based models, this is the kind of thing you might see. On the bottom end, you'll have CPU instances, a runtime environment with Python that is stateless, where the inferences don't impact each other. On top of that, you have relatively small artifacts, possibly on the order of hundreds of megabytes. And then sitting on top of that, generally a single model endpoint that is associated with a single relatively narrow task-based use case. As we move to the right-hand side, while some of these have been in production in different places over the last decade, FMs have expanded the need to move to this new stack, and we see a significant increase in complexity. So with LLMs, we now have multi-GPU instances with CUDA libraries sitting on top. In runtime environments that may be stateful, so if you think about KV caches sitting in there where each generation is impacted by the generations before and after it, and then model artifacts that can be on the order of tens of gigabytes, and then model endpoints that now can be either single tenant with a single endpoint or multi-tenant, where you may have multiple downstream users that are accessing a same model endpoint. And so this meant for us that we had two key problems to solve. So the first, we needed to enable this new infrastructure, delivering an FM inferencing stack from hardware all the way to our application layer, but then also aligning to the requirements that we already had in place. We have a well-defined set of production systems and pipelines, and we need to make sure that we were enabling those as well. This meant things like availability, performance, and the scaling of our platform, as well as ensuring that we are compliant with risk processes, cyber controls, and our multi-tenant requirements. So let me talk to you a little bit about the solution that we put into place. There's two major components, just like we had two core problems that we were trying to solve. On the left-hand side of this diagram, and I will jump into each individually, you'll see the core platform. So this core platform infrastructure already enabled many of our non-functional requirements. But on the right-hand side, we integrated SageMaker inference in the back end of this infrastructure to enable that FM inferencing stack. So this did a couple of things for us. When we built this architecture, and let me orient you a little bit to the central, to the core platform, we have a set of EKS clusters with tenant namespaces. This is where the models are actually deployed, and previous models would have inferred from. Below that, we have a management API service that actually does the model deployments and the management of the underlying infrastructure. By fronting SageMaker inference with this, we were able to do a couple of different things. One, we were able to use the same internally facing API gateway. This meant that tenants of our platforms were using the same endpoints. And so the experience was familiar. There was not a significant amount of infrastructure change that needed to happen. Tenants are also now still segmented by namespace. So we understood how to maintain that segmentation, and there was not significant changes that needed to be made in order to have multiple tenants on our platform. Lastly, we had to make some underlying changes to this core infrastructure. So if you see on the bottom, there's the SageMaker operator there. This is the SageMaker ACK. By integrating the SageMaker ACK, we were able to, from our Kubernetes clusters, actually deploy SageMaker endpoints. And then we would modify our tenant operator so that inside of each tenant namespace, there's a router inside of it. It would then tell the router to route a particular model call to a specific SageMaker endpoint, where previously you would have had a model running inside that specific namespace. On top of all of this, because we are running that infrastructure, we already had the overarching architecture in place to enable high availability across multiple different SageMaker endpoints in different regions. On the SageMaker side of things, the management API is provisioning SageMaker endpoints. In each of these SageMaker endpoints, we have GPU instances that are currently reserved via on-demand capacity reservations. As we all know, there is some level of supply constraints, and so managing across those supply constraints is something that we're continuously doing in the context of the platform. And when I talk about use cases a little bit, we have some fungibility there in terms of how we actually distribute the instances that we have available. We're provisioning those models into our tenant namespace and tenant namespaces, and they're accessed via Golang-based routers. At this point in time, we have deployed multiple different open source model families and use them in a number of different use cases. They're currently being accessed both by model developers as well as by end applications. So one addendum here, how do we actually think about getting a model into the production environment? So we have a relatively detailed model review and benchmarking process. This includes benchmarking models against external benchmarks as well as our own internal benchmarks. This ensures that each model meets the quality standards for Capital One related use cases. We're also looking to ensure that we maintain the minimum set of models inside of our ecosystem. We want models that meet all of the end user requirements that we have for all of our use cases. At the same time, we don't want to have a significant number of overlapping models because it makes it difficult to actually manage the infrastructure. It means that we have end users who are changing versions, changing models all the time. So we have a responsibility to ensure that that ecosystem is consistent and right-sized. Once a model is approved, it's stored, hashed, and encrypted in S3, and then access is only granted for uploading to our endpoints. This ensures that models are not tampered with after they have been tested. We're also using Amazon large model inference containers that are published from or pulled from the AWS public ECR. This was a significant help to us early on and meant that we didn't have to manage our own images, and then also meant that it reduced the platform exposure to vulnerabilities that we would otherwise have to remediate, both speeding our time to production as well as making the quality of life for our developers better. Okay, so we have this platform. How are we actually using it? So we have basically two primary patterns for usage of the platform. And it's broken down into, on the top, a production set of use cases, and on the bottom, a development set of use cases. The production system provides access to a range of different orchestrators and compute patterns in the app layer, in the VPCs, each model being accessed through our production model APIs. And then we have a separate one for developers in the bottom that enables both prototyping and development work to happen. The underlying infrastructure for both is, as you would expect, separated to limit blast radius for developers within our development VPCs and prevent them from impacting our production deployed applications. We also ensure that models are simultaneously deployed to both our development as well as our production clusters. This ensures that any work that is done in development has a clear pathway from the development environment into production. We have seen in the past when this doesn't happen, you can have significant breakdowns, especially with teams, say, expecting that there will be a production available model and planning and building towards that, and so we need to deploy them simultaneously. We also have separate onboarding processes for each set of clusters. For our developers, we are ensuring that they have the right use cases that meet our requirements for governance, and that they've been approved at the appropriate level within Capital One, and that we also have the right infrastructure available and we can support their throughput needs. In our production environment, we have a traditional software development lifecycle, as well as a set of model evaluations that are run before they are actually deployed. And then the infrastructure within each of these is optimized for use. So within our development clusters, we are focused on cost optimization as well as batching for throughput, with a lower focus on latency within those environments, as well as lower cost instances. In our production environments, we are organizing and orienting towards each individual use case, looking at use case throughput and latency needs, and then provisioning based on those requirements, as well as the cost constraints of the individual end user. The last thing to talk about here is in our development environment, we also have both logging and security review of inference to ensure that all usage of the models inside of our open environments meet Capital One standards for both platform usage as well as large language model usage. So we have built this basically two grouping architecture for our platform. But the integration of SageMaker inference on the back end had a number of positive impacts for us. So one, it had the development time from 8 weeks to 4 weeks versus an in-house built capability on an open source stack. The core stack worked out of the box with deep learning containers, so we knew that this had been prior tested and would be something that we could depend on once we actually put our models into the space. It also reduced our platform level vulnerability exposure to near zero. And then it's production ready out of the box with 99.95% availability SLA, combined with a multi-region deployment that met our overall organization expectations for high availability for serving of models in our production environments. And then lastly, and maybe the most important part for us as an organization to ensure that we could deliver this in a short time frame, especially as a highly regulated bank, and integrated with our inference infrastructure and governance processes that were already in place. So these are things that had been evaluated by our cyber and risk partners, and we knew that if we integrated those in the back end, the number of things we would actually have to evaluate and prove were fit for purpose would be significantly less. Some future directions. So as Venki and Amit talked about, there's a whole host of optimizations that are currently in progress right now. We are planning on using a number of them. So we're currently looking at using SageMaker inference components. We've done some evaluations there, and we expect to see a 100% increase in resource utilization, assuming we also have autoscaling in place simultaneously. And then with the inference optimization toolkit, both speculative decoding and quantization are things we are looking at. With speculative decoding, we're expecting to see about a 50% reduction in overall latency for particular classes of models. And then we're also evaluating 8-bit quantization with activation-aware weight quantization. So maybe a final call out on my end. I started with talking about Capital One's ML journey. We are continuing on this journey, and we're continuing to attract world-class talent across our organizations. We're thrilled to see in the last year that the independent research firm Evident Insights recognized Capital One as among the leading global banks in AI and as the top bank in AI talent. It's a testament to what our team has done, both building out our organizational infrastructure as well as achieving a number of different AI and ML related strategic objectives. If any of this interests you, please go ahead and take a look at capitalone.com/tech. Thank you very much, and I will hand it over to Venki now to close us out. I should do that.
Okay. So are you able to hear me? Thank you so much, Grant and Amit. And thanks all for joining us in this session today. Hope you found it useful. We are here to answer any questions right after the session, but we'll jump right into the Q&A session. But before we go there, please complete the session survey in the mobile app. That's super helpful for us. It gives us feedback on the session content as well as the presenters, and it helps us improve our content going forward. So please do take a few minutes to provide us feedback. Now, Q&A, so please feel free to ask any questions that you have. And I'll also hang out after the session for a while, so you can ask me questions there in person if you want to do that as well. Thank you so much. Thanks for the time.
Thank you.
Appreciate it.